Welcome, everyone. Welcome to Library of Congress's Preservation Week programming. We'd like to acknowledge that the Library of Congress sits on the traditional homelands of the people of the Piscataway, Nacotchtank, Pamunkey, and Manahoic nations. We acknowledge the traditional owners and sovereign custodians of the land on which we live and work, and we extend our respects to their ancestors and all First Nations peoples and elders past, present, and future. Welcome. My name is Jacob Nadal. I'm Director for Preservation here at the Library of Congress, and we're pleased to see so many people joining us coast to coast and around the world. It looks like we have 120 and counting here for a talk from Dr. Eric Monroe about understanding risks to collection through physical and chemical analyses. We do scientific analysis on our collections and materials we use in preservation for a wide variety of reasons and in a wide variety of ways. And I'm really excited for Eric to be able to talk to you about some of the capabilities we have here and have developed, and some of the capabilities that are becoming much more usable and useful to operations beyond the Library of Congress. We'll have additional presentations tomorrow, and of course, Amelia will be posting throughout this talk to share links to our blog, our reference site, and our resources. We're glad to have you here today, and we encourage you to be in touch with us all year long. Thank you, and let me hand it over to Eric.
Thanks, Jake, and thank you everybody for joining us. As Jake mentioned, I'm going to be talking about how we're using physical and chemical analyses to understand risks to the collection. So before diving into all of the details and some of the science that we're doing, I wanted to kind of start off by placing this into why I particularly find this so utterly important. So the Library of Congress has a huge, diverse, and varied collection of items. We have over 175 million items in our collections. This includes everything from books, audio materials, manuscripts, maps, microfilms, sheet music, moving images, photographs, et cetera, et cetera, et cetera. And so having this diverse, varied collection presents a number of challenges, particularly as with the mission of us being a library centered on the direct use of the collections. Just the sheer diversity of the collections produce a number of risks, from systematic risks of the environment, security, emergency response, the sheer logistics and inventory management that's required to deal with such a large collection, while still having all of these different materials made of all of these different or different collections made of different materials, different formats, have a large variation in the ways that they can be damaged, decay, degrade, or even just age over time. That's kind of what the Preservation Directorate is set to do. We want to make these materials available from here near into perpetuity to be available for use with the public. And with that, not only do we have this diverse set of collections, but these collections live in really many different environments. Everything from on permanent exhibition, like the Jefferson Library in the top left corner, temporary exhibits, short-term exhibitions, or even housed at Fort Meade in our high-density storage there in the here, or on Capitol Hill in bookshelves, or in storage areas. So here in geography and maps. Here's a secure storage vault for music and some of our large flute collection. And so one thing to think about is not just we have this diverse set of collections, but they live in many different environments. And so when I look at that, I think about, well, what among all of the things that are here in these images could be a risk to the collections? I'm going to take a drink while you contemplate that, and then I'll give you my answer. So when I look at this, and having been at the library for 8.5 years, and in the role that I've been serving, and overseeing our quality assurance and testing of materials, really the answer is pretty much yes. So materials, the collections themselves can be a risk to themselves, how we store them, how we exhibit them, everything that basically a collection object may quote unquote see as it's being stored or exhibited can serve as a risk. And so one of the things that we're doing, particularly in my group, is to try and understand the risk to the collections by doing scientific testing. In years past, we have our traditional quality assurance program, and we have a materials testing side of this, where we're really wanting to understand what the risk of collections from the materials that are surrounding it, either as storage and rehousing, as those on the left with all of the boxes and the labels, Mylar, to materials that are used in building exhibition cases or secure storage vaults or the large store facilities up in Fort Meade. So we've been looking at how can we test these materials in order to best understand the risk there, and then by either environmental controls, engineering controls, or product selection, try and reduce that risk to the collections over time. Now, this is a program that's been around for quite some time. In the past couple years, we've been combining these two branches of both the traditional QA program and the materials testing into something that we can then start to try and figure out how we can improve its performance. Over the pandemic, we consolidated a number of people in PRTD to try and figure out kind of top down, how can we improve this program? We're starting to implement all of these changes. So right now we've got a more rapid response with a faster turn time, largely by improving our internal workflows at this point in time. One of the things that we've done with that is started to consolidate all of this testing into one physical location. So this is the images from our lab here in Madison and the G52 lab when the mass deacidification contractor moved their on-site deacidification program out of the building. That left this room in my lab open. So we've been able to repair the flooring and then start consolidating everything. So now this testing can happen in one space rather than 3 spaces across 2 floors of the Madison building. It's been a big benefit, and we're now starting to think about how we can do this going forward and other improvements we can make. Some of that's going to be including reviewing and updating our specifications that we'll talk about here in a couple of minutes. We've already started doing some of that to get our specifications more in line with international standards, reviewing our testing processes. So again, we can try and be more agile in response to those that need this kind of testing, moving in-house testing protocols. So that large cardboard box back there is a new instrument that will allow us to do some testing that we've previously had to send out. So now, again, we can do this in a more agile response to those that really need to have the results on whether or not a material that need to be used for some sort of rehousing project can have a risk or not, or if it will serve the purposes. We also are looking to improve our reporting processes and make it easier to request. So I'm all about trying to lower the barriers to entry so we can keep our people very busy and testing all of the materials that I'll talk about in the rest of the talk, all while trying to understand what these materials might have as a risk to the collection and how we can best mitigate that. So first, I want to talk about what is traditionally the quality assurance program. So these are materials that are used to often through the Preservation Directorate's Preservation Supply Catalog. So these are everything from cardboard, boxes, sleeves, both Mylar and paper-based, all of the labels. If it's going to come in contact with a collection object during rehousing, we're going to test it. We test it before we award the contract and every time an order comes through to ensure that things don't change. These all have published specifications that are available on our website. Sometimes they're a little outdated. So if something looks quite old, please get in touch with us. I've got our email at the end, and we can send along the most recent ones as needed. But having published specifications makes this very simple for us. We can then just go through and run through all of our chemical and physical tests that are needed to ensure that the various specifications are met. Oftentimes this is doing a lot of basically torture testing for fold durability and tensile strength and all of those kind of physical parameters that you might think of if you're, let's say, a paper folder. But then we also do a bunch of chemical testing to ensure that the materials themselves aren't acidic and so they wouldn't damage the objects within, or that they have sufficient alkaline reserve, so they will, even as the paper that makes up that folder might start to degrade somewhat over time, it won't become acidic. We do a lot of bleed testings to ensure that we're not going to have color transfer for some storage object that is colored. So we run the gamut, again, all to ensure that we know what's going to happen over time. Now, most of the materials that we end up testing meet or exceed these specifications, which is a good thing. But even if one of the specifications might not be met, oftentimes it's something like stiffness, so the folder might be a little more floppy than the specification provides. We provide this information to the end users, and then those kind of decisions can be made on that basis. We're not there to say yay or nay. We're there to provide information, so those that really need the materials can enter this with understanding any risk that might be present. That said, occasionally we do come across some quote unquote gems. These are not necessarily good things, but they're there. It's very important to understand and to show, in my mind, what happens if things were to go wrong. And so where we can serve as the backstop to ensure that any changes in the manufacturing process or the materials don't provide an undue risk. So here are some label stocks that came in. A and B, I believe, were pre-award testing for the contract in the first batch. They passed this migration test just fine, where you can if you squint, you can kind of see where the labels were in contact. But then we started to see some other shipments. So a different shipment came in, and those labels, the adhesive had changed. This was even unknown to the supplier. It was their supplier who had changed what they were providing to who we were originally purchasing from. And here, we're the Library of Congress buys labels in many thousands at a time. And so by catching that this label stock had changed, the adhesive had changed, and would over time damage the collections, by highlighting this and end up kicking this order back and saying, okay, this is an undue risk. We were able to prevent damage to many thousands of objects. And in this case, it surprised our supplier. So they went back to their suppliers to try and figure out what was going on. And then eventually changed back, found a different adhesive to then mitigate this problem so we can move forward. Another situation that we've had are pamphlet binders. So in this case, the dyes that the dyeing of the fabric that connects the front and back of these pamphlet binders, had been seeing a couple of years ago that all of a sudden everything was failing bleed. Those fabrics had the dye wasn't well set. So in case of, for instance, if there was a water issue or a water incursion, the dyes could migrate to the collections. That's not what we would deem to be a good thing, something we want to mitigate. But at the same time, just being in contact with the collection over years could also have ended up with this style of migration occurring. So these are all problems that we really want to mitigate. And so when we get something like pamphlet binders, where there are multiple materials that go into their construction, we oftentimes are deconstructing these materials so we can test not just the entire lot, but the individual components to identify where that risk might be. So then that can also go back to either the end user or the manufacturer to try and mitigate those problems. We also do testing for paper enclosures for negative strips, for instance, where we do something called the photograph activity test. In this case, while it's kind of hard to see, both the paper and the adhesive for these enclosures failed this testing. So what this does is you're exposing both a piece of photographic film and some paper substrates to the material that you're testing, and you're looking for any changes in color or modeling. Now the adhesive, you can see that's pretty evident that that's something we don't really want around any of our photographic negatives long term. And so it's, again, it's another thing where we can not just prevent damage, but then go back to the manufacturer, have them change things. Oftentimes that leads to them changing what they're offering product wise. So not only are we able to help our collections, but hopefully when we find these issues, it can help other people's collections who do not have the capabilities, time, or resources like we thankfully do to do this level of detailed testing. So that is kind of our standard long-term quality assurance of storage materials. The rest of the time, I want to talk more about how we have been bringing and expanding our testing to go just beyond housing materials and instead expand it to materials used in the construction of the library spaces as well as exhibitions. So this is covering everything that you might imagine. We look at fabrics, paints, gaskets, sealants, spray paints. There's an acoustic tile in this set somewhere. Carpet, floor tiles. It's really run the gamut and has been quite intriguing to see. And these kind of materials produce their own specific list of challenges. This is my wordy slide. I hate wordy slides, but it highlights kind of the number of challenges that even just standard material use in the library museum situation is completely different from the way you might think of it as something that you might be using in your house, for instance. So obviously bad material selection can cause undue harm and risk. That's why I'm here talking. This is what this entire talk is about. But in reality, libraries and museums are a very small market, so we don't have a lot of purchasing power. And while we could make specifications for these kind of materials, tightening those very careful or to very tight limitations can really just make it so there's nothing available on the market. We see this sometimes with the housing materials. We're trying to prevent that by ensuring that, but particularly if you start thinking about, okay, what do we specify in a paint? There's really not an awful lot there because we're not going to have somebody that's we're not going to have a company making up a paint just for use in our exhibitions, for instance. In addition, just looking at a safety data sheet, for instance, doesn't really help define what the risk of damage to collections are. And in reality, oftentimes what might be safe for humans, so think of a green paint or some sort of, I will show in a second, a floor tile that is made from all natural materials, etc. While that sounds great for people and the earth, it might not be good for the collection. So there's a balance that we have to play there. And as commodity goods, the stability of the product formulation often changes. This is due to the manufacturer making developments for improving their environmental processing on their end, health and safety and cost savings, because a company is going to company. But at the same time, sometimes the materials have poor stability over time. Because they're commodity goods. They're not meant to last forever and ever and ever until time perpetuity. So these are all things that we really have to think about. In addition, like the previous methods I showed about looking at material properties and risk for storage, that might be good for papers and cardboard and mylar sleeves and things like that. But when you start thinking about everything that might go into renovating a space from raw concrete block walls to a secure storage facility, there's a lot that would be missed there. We're not just looking at the physical and chemical nature, but if you think about what might come off of those compounds as they change over time, i.e. volatile compounds that could be released, that tends to be something that is more important in this situation where we're looking at materials used to build storage spaces and exhibition cases versus the direct storage of the materials that I've been talking about. So that's a long-winded way of saying there's a lot of problems and challenges. Well, we do have testing methods that can address most of these. The traditional test is the ODDI test. It was developed in 1973. by a guy by the last name of Audi. And so in our iteration of this test, we take the material that we want to test. Here it is this black adhesive. It's just on a piece of aluminum foil, into a beaker with a piece of silver, copper, and lead. We then add some water into the overall jar, seal it up nice and tight, and put it into an aging oven at 6 degrees Celsius for 28 days. When we then go back and look at that in a month, we want those materials to look all nice and shiny, just like they did when they went in. What we don't want is we don't want the lead to start looking like copper. We don't want the copper to have big spots. We don't want our silver to tarnish. It's really a corrosion test. It's imperfect for a lot of our collections and determining that risk, but as a lot of what we have isn't metallic, but it's the library and museum kind of bar standard. And it's really useful and predictive of risk. But as a material scientist and analytical chemist, it's kind of unfulfilling to me because I always want to know, why does this fail? So I'll get to that here in a couple of minutes on how when I came to the library, I brought some knowledge and some testing that I had done in my previous life in industry to then understand what's going on. But as a transition to that, I want to share what is my quote unquote favorite failure. So this was a floor tile that was proposed for use in the music division's SSF development. It had all of the green labels on it. It was made from entirely natural materials. It had no plasticizers. It was entirely recyclable. And it just went on and on and on. Well, when we did the Audi test, all of a sudden it grew a 3 centimeter plus long white growth. It looked kind of like the carbon snake fireworks coming off of that lead coupon. This would have been particularly challenging and probably not a good thing when to store our music instrument collection with all of the the leaded solder joints, things like that. This was something of definitely an undue risk. But then the question really was, well, why is this failing? At the same time, we're doing another test that we've developed and adapted based off of some quality assurance testing that is utilized in the automobile industry, either these standard tests, VDA 278, which is the European version of the, and one from in the US, that's General Motors, where we're using a technique called thermal desorption gas chromatography mass spectrometry. Basically, we take the sample material, shove it into a little glass tube. It then is put into this little oven that's sitting on top of the instrument that heats up to 90 degrees Celsius for about half an hour. Then that allows all of the volatile compounds that would come off, all of the smells that might come off of a material, you can think of it that way, to come off of that material. Those chemicals are trapped onto a liquid nitrogen cooled inlet. Just below that, after all of the material is desorbed, we heat that inlet up. So each of the compounds then enters the gas phase again. It is separate. Each one of those compounds is separated over a column within this oven. And so in a perfect world, they come off that oven or come off the column one at a time and are detected with a mass spectrometer over here. It's an entirely enclosed system. And so if we do the desorption well enough, we have a semi-quantitative measure of not just what might come off or what will come off the material over time, but how much. We can set this, we run a regular toluene standard, so we can report everything as equivalent to toluene. It's imperfect for, let me just leave it at that. It's kind of an imperfect measure, so we're not saying, that we know a hard fast, this is the quantity, but it's very useful in understanding if there's a lot or a little. As none of these things have specifications, as I mentioned before, it allows us to think not just, okay, is there something that might cause problems, but well, if we're looking at a sealant, for instance, it's going to be used, and there's going to be about a cup of it used in the latest module at Fort Meade, which is 5-6 stories tall and has a footprint the size of a football field with high airflow. That's much different than if the same amount of material is going to go into an exhibition case that is entirely enclosed and has 10 cubic feet of air. So we can start to think about, okay, not only do we test this, but what's going on. So I'm kind of showing this backwards. When we did the thermal desorption of the tile, we saw this. This is the output of that previous test. Don't get all bogged down in all of the lines and everything else. I'm going to try and summarize, and this is going to be kind of what we're looking at through the rest of this talk. But for those that might not be familiar, we have signal on this axis, time. So this is that separation over the column. And each of the peaks is an individual compound. Sometimes they're well resolved, which is great. Sometimes they overlap, which is a little more problematic, but we can get a really good understanding of what's going on. So when we looked at this tile, we had 100 part per million of fatty acids. So those are all these with the hashtag on them. And the thing is, this perfectly explains what we saw and then confirmed with X-ray diffraction, that white growth off the lead was the production of lead white in situ. So this is lead carbonate and lead hydroxide. So we're in a saturated water atmosphere. Fatty acids have this carboxylic, it's a carboxylic acid group that would interact with the lead surface. So it was really growing and making a stalactite from the lead coupon itself. So we saw this and predicted that that lead coupon was going to fail. And lo and behold, it did. So this was several years ago. We've been doing both the AUDI test and the GCMS thermal desorption for the past 7+ years. And so we're linking those two tests together. And so we have a really good way of thinking about and having some chemical intuition that we've seen these materials in the past that have been problematic, which is useful when we start thinking about being able to speed up our testing program. If we see a big red flag, for instance, we can reach out to those that were asking us to do this work and say, hey, we're probably going to have a problem with this. Let's start looking at alternative materials. We'll have a confirmation. When you're thinking about those kind of situations, even just having a potential red flag can help, particularly when we're dealing oftentimes with construction and exhibition schedules in this case. We've also been able to be proactive in this part. So in 2018, 19, 20, or yeah, somewhere across there, a number of cultural heritage institutions really across the world were seeing that some of their collections that were in some new cases were having these white crystals start forming either on the interior of the cases, interior of the glass, or on the collection objects themselves. This was identified and reported by a number of different people to be related to the presence of this TMP-all in one of the adhesives that was used in the construction of the exhibition cases. Now, these cases and all the materials used to make these in cases had undergone the standard AUDI test, and they passed. Really, they passed with flying colors, from what I have been told. So what was happening is this is a light stabilization reagent, and these other researchers had found out that when this TMP-all would enter the gas phase in the exhibit case, it was interacting with other compounds that had off-gassed from other materials used in either the construction of the case or the contents of the exhibition case themselves, the collection objects themselves. It was only then did they interact, react, and form these various crystalline deposits. So the AUDI test would be blind to this. So I ended up buying and ordering in a number of adhesives, hoping that I could come up with one that had this material or this compound in it, and we are able to detect it. So this is another one of the ways that we can look at this is if we know failure modes and we know known bad compounds, rather than waiting 28 days, or in this case, where we would still be blind to it, we can detect it using this thermal desorption technique. We thankfully have not seen any of this material and any of the adhesives used in any of our exhibition cases, but it's something good for us to have in our back pocket, should it ever rear its ugly head. Another material that we see far more often are these PVC boards that are used almost universally in the construction of exhibition cases interiors. There is one known problem with some of these PVC boards, and typically it's actually the ones that are on the higher end. And that's the presence of this ethyl hexyl thioglycolate compound. It's used as a heat stabilization reagent. So the PVC boards under normal commercial use, not necessarily the library style usage and museum uses, but what these boards are normally sold for, they would last longer. And so there's this presence, and this wasn't something that we identified. It was originally identified through some research done at the Indianapolis Museum of Art and with a professor from Butler University, which is where I got my undergrad degree, which is a completely different fun story, in that the two groups, both the library and Indianapolis Museum of Art, ended up largely developing the same style technique as what we're talking about now, this thermal desorption technique, to try and identify these problematic compounds. Even though when I was going through school, neither the professor nor I knew that these fields even existed. It's great fun. But the Indianapolis Museum of Art needed to figure out what was going on, as they have a large silver collection, and they really were starting to see tarnish after several months of installing the new exhibit in their new encasements. And it would all track back down to this ethyl hexyl thioglycolate. Now, this does tarnish the silver in the Audi test quite easily and rapidly, so it's very visible that there's a problem. But again, this takes 28 days, and with exhibition schedules and particularly rotating exhibits, if the encasements aren't being made particularly early on in the process, this is something that we can tease apart very rapidly. This showed up in one of the exhibits a couple of years ago, where we finally got the samples to test on a Thursday, and they said that the case manufacturer said they had to start on Monday, otherwise they weren't going to be able to meet the exhibition schedule, which was a non-starter. And we did the test, and lo and behold, it had this ethyl hexyl thioglycolate. So we said, well, okay, here's the problem. We've tested these different boards over the course of the past 6 months or so, and they've been would have passed this test. Maybe you should go and buy a supply of that over the weekend. If you give it to us on Monday morning, we can actually have answers to you thumbs up, thumbs down by lunchtime. The new board looked great, had passed, and the exhibit opened just fine. Of these 4 that are here, 2 of them have the ethyl hexyl thioglycolate, and 2 of them do not. It's not evident just by looking at them whether or not these compounds would be there and it would cause problems. So it's testing like this is really important and helpful in giving basically red flags. Another way that we've been using this is trying to figure out really what can we have as alternative compositions. Again, we're materials and product availability changes. So for the past decade or so, the library has largely used one approved paint, particularly in exhibition spaces and cases. Unfortunately, that product was removed from the market, discontinued about 1.5 or 2 years ago. This is what it used to look like. It was beautiful. There was very little, if anything, that was coming off. Even the suggested replacement, which is here in gray, has many more peaks at much higher. And then 2 alternatives also suggested from the manufacturer, who said, this is as close as we have to the previous, still has these other materials that we then have to go through and test for. And some of them could potentially have problems. So this material here is a biocide, but it has what could be a reactive sulfur that could then lead to tarnishing of materials. So there's a number of things that we need to look at. And we can use this kind of as a quick screen to, if we can't find the perfect thing, find what might be good enough or what is least bad, and then utilize other techniques that others have developed, that we have looked at, that conservation has looked at, to try and mitigate these kind of risks. If we can't do it just with product selection, if we know what we're up against, we can try and adapt and develop engineering controls to then help mitigate that risk. And then sometimes we get surprised when even what was thought to be the same is not the same. These are 2 suede fabric samples that are used in mount making. And the old stock came to, or the supplied suede came to us relatively recently, where the material had been reported previously a number of times to have passed the Audi test But when we looked at it through the thermal desorption method and ADI testing, we were seeing results that were inconsistent with what had been previously reported. We then talked to the supplier, the person, and they found some old stock of the same brand and was supposedly the exact same material. We did that testing and we get completely different results. Another one of those big surprise to those that the suppliers even. So it seems that their suppliers have completely changed up the way that they're making the suede. And we did some other work that suggests it's even a completely different fiber blend between what was old and what is new. And so it's another one of those things where we're seeing that not just things were supposed to be the same can be completely different. And it's only with testing that we can understand what that risk is. With the supplied suede, not only did we see it fail on the lead coupon, but we're seeing again some thiazoles, so some sulfur containing compounds, carboxylic acids. These are all things that are really on our naughty list that we're trying to look out for. So that's the materials testing side of things. And we've really been able to not just look at using thermal desorption, GCMS to look at materials directly, but by changing some of our sampling processes, it allows us to be flexible on using the technique and look not just at materials, but we can go and take battery powered man pumps and little sorbent tubes and take them outside of the lab. So we can go and look at collections or exhibition spaces. For here, I'll talk to this in a second, we're sampled from within the Jefferson Library encasements, as well as individual collection objects to try and understand what's going on in various cases. So the first and one of my favorite stories from my time at the library is the Gutenberg Bible case. So a number of years ago, the Gutenberg Bible was getting a new encasement. So if you've been to the library in the past couple of years, you've seen this. The encasement is entirely enclosed and sealed tight. It has its own temperature and humidity controls to it. And as the library and conservation goes in and changes the pages on the Gutenberg Bible regularly to prevent risk from light exposure, this entire front door has is gasketed to allow ready access. So we went through and tested all of the materials that make up the interior of the encasement, as well as the airflow through the temperature and humidity control system. And really, we only had one item of concern. One material gave us pause, and that was from the gasket that was originally proposed. When we did the direct thermal desorption, it looked nice and clean. There's only really one peak outside of some of these very low volatile, high molecular weight materials. Things out here are much less concerned than those are within this portion of the chromatogram. But when I was shown this data, first it looked like, okay, well, this is relatively clean, should be pretty good. And then I saw the identification that the software gave out to me, and I recognized this compound, but couldn't quite initially place it why. Then it dawned on me, and then I checked Dr. Google that confirmed this phenylisocyanate compound was utilized in early protein degradation experiments for sequencing. So this compound is known to literally chew up proteins bit by bit. One of the things that's special about our Gutenberg Bible that we have in our collections is it's one of few that are on vellum. So this is parchment calf. It is therefore entirely made of protein. So this is something that was of great concern, as while this might not cause a failure in the ADI test, because we have proteinaceous material in that case, this is of great concern. To test this, we went into our store, or into our samples that PRTD maintains for this kind of destructive testing, where we have modern parchment. We incubated this in a small jar with a little bit of water at just above human body temperature, because parchment doesn't like to get particularly warm. And over the course of about a month, we were able to see that, yeah, this amide amide band and this Fourier transform infrared spectroscopy experiment was dramatically different from the control to what we had incubated with the gasket. As parchment ages and begins to degrade, this is the kind of shift that we see in the amide tube on it. It decreases and it shifts in wave number. We took the same FTIR over to rare books and did a bunch of experiments looking at parchments that have been naturally aged from medieval times to more recent. And yeah, we see this same kind of technique, and this level of change is equivalent to many, many years, well north of 100 or 200 years of natural aging. So it was a really good thing we were able to catch this, go back and then suggest that the gasket be changed out. It was. So now the gasketing is, I believe, a silicone elastomer, which we then tested and saw no problem. So when we oftentimes are getting ready to have collections go into these encasements, we can also take that battery-powered man pump, put it into the encasement, and then check to see if we are only going to detect materials and compounds that we would expect to see. In the case of the Gutenberg, we really weren't surprised with anything. The only things that we weren't expecting to see was the limonene and the isopropyl alcohol, and some of the pentane. Those all made sense as we did this right after they had taken care of and had finalized the installation and cleaning of the encasement. So they used isopropyl alcohol to clean the glass. Pentane is something that is a human metabolite. It's in our breath. And limonene, because they had been cleaning the Great Hall, because Congress was coming to take their freshman picture that evening. So it all made sense. The Bible went in, and it's been a great success ever since. I mentioned we've also looked at the Jefferson Library encasements. This started as there was some concern in odors in a couple of the cases themselves. They're very well sealed, and they're on permanent exhibition. So when we went through and tested, I think it was 20 of the 22 cases or something along those lines, what we saw was very similar across all of them. And I didn't label these peaks here, but they largely correspond to what we'd expect from long-term paper degradation. Paper ages, old book smell, that's what we're basically seeing here, which was good in a way that it said that those two sections of case that were of concern, really, it was just a slight variation in levels of some certain compounds. So it's probably something that we as humans, our nose was more sensitive to rather than a big red flag. But they were relatively high levels, quite high levels of volatiles. And so these results were able to inform the way that the new cases for the Jefferson Library have been developed, and added some engineering controls to help prevent kind of the buildup of these volatile compounds, which can be catalytic in further degradation. And this is all as part of the new cases that'll go into the new visitor experience over in the Jefferson building in the next couple of years. We can also look at sampling volatiles from an individual collection object by either putting a hole in the blue board boxes that often house collections, or snaking in a small stainless steel tube to sample from a case a collection object in its housing. Here is a Japanese print that had a odor almost of gunpowder or smoke. When we did that test, really from a blank box or one with the prints, it was very similar. Outside of, there were a couple of peaks that were present only in the prints or in the sample from the print containing box, which were had a number of sulfur compounds. What this indicated was that it was likely a degradation of the orpiment pigment that was used in the production of the print. And so rather than housing this print with many others in a single folder or a single box, it has been isolated and should be being stored on its own, so it is not of a risk to its neighbors, basically. So that's sampling from collections. We're, again, always trying to improve the way that we do things. oftentimes when we've been doing all of this air sampling before, just been using the little battery powered pumps and the sorbent filled tubes. We can only pump so fast there. It's about 100 milliliters a minute. So we'd have to sample for multiple hours. This is problematic if we have to get in and out of an encasement, for instance. But what we found is we can utilize these air sampling bags, where we can put it into this black case, pull a vacuum on the case, it expands the bag, sucks the air from the surrounding area or the tube that we connect to it, so we can still snake this into certain areas and collect those volatiles, take it back to the lab, and then do our slow process. Now, into figuring out what's the best way of doing this, there's a number of air sampling bags on the market. And we found that some have background peaks that would mask compounds that we're particularly interested in. So it's something where we have to make sure that we're using the right materials, so we're not adding ambiguities into our testing as we can. We've done this in a couple of different places. One of the most adventurous was sampling from the air handlers at Fort Meade. So this involved me climbing ladders and going into portions of an air handler about the size of a school bus. But it allowed us to look at and understand the effectiveness of the air handler and its filter train to enable to inform future module designs. So here's just the return air where we see, a lot of compounds that we would expect to see from large paper collections. We see the acetic acid, ethyl hexanol. It's nothing we wouldn't expect to see. When we sample from later in the air handler, so after it's gone through the various passive and active filtration, we found that, well, yeah, our current filters are performing very well to remove both the internal and external pollutants, as well as identified some potential design improvements that the Architect of the Capitol and the Library of Congress can add to future module designs and air handling designs, and possibly retrofit those that are existing to improve efficiency, cost efficiency, et cetera, without actually increasing undue risk to the collections. So we can do everything from looking at how materials can potentially add risk to collections, understand why that is, to try and stop that ahead of seeing a problem a number of years later. But then by applying a number of testing methods, we're able to inform, predict, and explain what that risk might be. We don't want to be the people that say no to everything, because, well, if there's a risk to certain kinds of collections, that can be discussed and understood. And so what might be a risk to some collections might not be to others. And so that's that discussion that allows for the flexibility across the library that kind of builds upon what I started off with, which is the great diversity of the collections that the library has. Trying to be flexible is kind of key when we're looking at things, particularly where specifications don't exist. And so it's only with understanding the physical and chemical nature and how degradation of certain materials can relate back to and situations that the more I start dealing into it, or look more and more daunting day by day. But because we've been doing this and we do this so regularly, we do have a pretty good understanding for what kind of those red flags can be. And so I said a number of times that here's our contact information if you have questions, particularly with our materials testing, prtd@lsc.gov. That'll get to some of us within. And particularly for those of you that are here at the library, if you have materials that you use that are not from the preservation catalog, and you'd like for us to test and look at those, even if we haven't in the past, please reach out to us. We're happy to do such things. We don't do external testing for others, unfortunately, but we are working to try and being able to share what our test results are going forward far more broadly than we've been in the past. So with that, I need to thank a number of people, particularly those that do all of this quality assurance testing for me, being Kelly, Chris, and Michelle, a bunch of PRTD staff that have been helpful throughout, as well as members from the conservation division, particularly Nancy, Ken, and Elmer, who have really been helping drive us over the past number of years in developing those thermal desorption protocols as we look to understand what's going into the construction of exhibition cases, buildings, renovations, and how those may affect the collections long term. With that, I will stop, have a drink, and then happy to answer any questions that may have come through. Thank you.
Thank you so much, Eric. That was really interesting. There are links to all of these web addresses in the chat box. And if you have any questions, please put them in the Q&A section because it's just easier for me to see. And we already have a couple. So number one, can the Audi test be accelerated by using gold wire and making use of the galvanic series to accelerate the less noble metals decay?
It might be able to. One of the situations there is you're looking at the three different surfaces were chosen as Audi was developing those for looking at and predicting problems for his coins of antiquity. So those were the metals that were most indicative for that. They do tend to be pretty good sacrificial components in that each one reacts to different types of compounds and chemicals differently. Using a gold wire, I mean, that's going to be inert, so you might be able to drive things differently by applying a potential, yes. Doing some electrochemistry, but it's also in air, so it gets really complicated at that point in time. It's really more complicated than it is. It's an interesting thought, but I haven't really thought about that in detail and have to go back to my previous life as an electrochemist, which I'm a little brain dead at the moment to be able to do on the fly.
Okay, thanks. And do you put pollution scavengers in cases? Would static Purafil Puricol work in a case, or microchamber card or carbon cloth, something like that?
All of the above. Yes, we've done that. Our encasements typically have silica to help keep the relative humidity constant. We've done work and show that even though silica do serve as a pretty good sorbent, things like Purafil, which is a impregnated active filter, we've shown for a number of materials or compounds of concern can be quite useful in that what that does is instead of like a carbon cloth or something like that, when a compound interacts with that surface of the Purafil, the active component of the Purafil will oxidize and literally chew up the compound. So it's not just a sorbent, but it can also degrade the compounds of concern. So it works quite well. And yes, we have put those into a number of cases over time, particularly when we see something of concern.
Okay, great. And are there any other institutions using the air sampling method to your knowledge?
There are a number of places I know that have at least wanted to, and using this thermal desorption style technique from materials has gained quite a level of pickup in some of the larger institutions across the world. So yeah, it's something that people have seemed to really take to. And it makes me very happy that I've been able to bring something from a completely different world that I've been through in my career into what we do now. And people are now taking this technique, and we found that it can be quite generalized. So it doesn't really depend on all of the minutia and the equipment that are used to do it. We might see different levels of different compounds, but on the whole, in a couple of round robins through the AIC materials working group, we've been able to show that really just doing some version of thermal desorption is capable of giving very similar results across the board. So it's something that's in the process of being adopted in a number of different places. So it's quite nice that way.
Okay. Do you have any recommendations for how someone should vet private labs that they might hire to do TD GCMS testing?
One thing to look at there would just be to ask if and see if they do anything with the automobile industry. So this technique was built upon when I worked for a chemical floor covering and textiles company before I came to the library, where the company was making some additives to go into foams that were going to go into the headliners of automobiles, and automobile manufacturers know that new car smell is not necessarily good for you. It's also problematic that it can form the haze on the interior of the windshield. So these are standard tests that a lot of for-hire labs will likely do, particularly if you find those that work with someone in the automobile industry or want to get into it. The equipment itself is kind of pricey. A GCMS is going to cost you north of $100,000. The thermal desorption rig is going to be a couple of tens of thousands. So it is a high buy-in. But I know there are a number of places that will do it for hire. That's something we had to do once early in the pandemic when we didn't have access to our lab. We found a place just outside of DC that was able to do similar testing for us.
All right, thanks. And with those price estimates, you answered a second question as well.
I cheated, I saw it come by.
All right, so how challenging is the development of an effective TD GCMS method and identification of the compounds associated with the different peaks in the chrome?
So the identification, we utilize a standard NIST library. So this is something that we just tell the program, hey, what is this compound? And it pings a database that we have that has several 100,000 compounds in. So the identification of the individual peaks is typically relatively easy. If it's not a very good match, oftentimes we can tell, okay, it has these chemical moieties and get a pretty good idea of not the exact compound, but the family of compounds that might come from. In developing the method, the largest and most important thing, particularly of the direct thermal desorption, is sample preparation, because we're trying to drive off all of the volatile compounds. We can test that by running the same sample a second time, where if we don't get everything evolved, then we'll see the same peaks again. Or if we're hitting it with too much temperature, for instance, we might be degrading the sample itself. Neither of these is a good thing. So outside of doing things like cryogrinding to make small samples, we tend to either try and do a film if it's a paint, or take very small slivers of something. If we still see problems, we can grind it up. And then it's a matter of adjusting time and temperature more than anything. And we do a standard GC separation. So it's surprisingly easy, given some of the other tests that we end up doing and trying to develop. Like I said, it's built off of an international standard. So we do some small tweaks every now and again. We see red flags, but otherwise we're largely following at least the first half of that VDA 278 method.
Okay, great. I'm typing an answer about housing methods to this one question, but they asked about binding on comics that fall apart easily. Have you seen anything in your testing that relates to that? Like I said, I'm typing up an answer about housing protection.
Not in what we have done. There's a number of other things that my group and conservation have done over the years in looking at how to repair bindings and things like that, and those adhesive things, but that's not something that we've utilized any of this work as part of. No.
Okay, and I think that is it for the questions. So remember, if you do have any questions in the future, there is the prtd@loc.gov email directly to the Research and Testing Division. But also, you can always go to the ask.loc.gov/preservation and for any preservation related question, and we can get you to the right person to help answer any of your questions. And then always check out our blog. We have a lot of interesting stories related to research and testing, as well as our other preservation activities. And yes, that should be it. So thank you all for coming and viewing our thing today. Sorry, I have trouble typing and talking at the same time. But thank you very much for attending today. We really do appreciate it. And yeah, so hopefully we'll see you tomorrow. Have a great day. Bye.
Thanks, everybody.